Okay, we're on chapter 15, and we started talking about solutions a little bit more. And we talked a lot about how the idea of like dissolves like. And really, what that means is, what we talked about is things that use similar sort of intermolecular forces will usually be soluble in each other. So, if somebody's using hydrogen bonding and kind of comes across somebody else that uses hydrogen bonding, they're going to be good to go. Something you dipole, dispersion forces and dispersion forces, they're going to be pretty good. So the idea there is essentially you'll see solubility when you have something that is polar and polar comes together. They both will be using the same type of intermolecular force. When something that's ionic and polar come together, they also will do good. They'll do some type of ion dipole interaction. Here, they'll do some type of either hydrogen bonding or dipole dipole. Here, they'll do some type of ion dipole interaction, which will make them soluble. Also, nonpolar things and nonpolar things will be soluble in each other as well. They both will be using dispersion forces. So, we again only really run into sort of problems with solubility when we sort of cross over. So again, when we really kind of take a polar thing and a non-polar thing, we're going to get some not really good mixture there. Again, because the non-polar is going to try to use dispersion forces, which is its only source. The polar guy is going to use either hydrogen bonding or dipole. And again, these things are very different types of interactions, and they're just not going to be able to kind of maintain that interaction and mix together. So we do see that intermolecular forces playing a really big role in how one molecule can interact with another. So again, as I mentioned, they have similar type of interactions that they do with themselves. They will be soluble with somebody else. Um, we also talked about saturated solution. Saturated solution, again, is a solution that has the maximum amount of solute that will be dissolved. And we also have, thank you, an unsaturated solution. No, you're good. Which is where you can still dissolve solute. And it can continue to dissolve that solute, and it will dissolve till you hit a saturated solution. We also, like in the lab, and talked about did a supersaturated solution, and supersaturated solution has way too much solute dissolved in the solvent at that given temperature, and it becomes a very unstable sort of solution that occurs. Remember again that when you have a solution, there's two parts. There is the solute, which is the smaller part of the solution, and there is the solvent, which is the larger part of the solution. So those two things together make up a solution. All right, any questions on any of that stuff there? All right, now that we talked about again some of this ways that solutions can interact with each other, we're going to talk now about some concentration type units that are associated with solutions. And the very first type of concentration unit we're going to talk about is a percent mass to mass unit. And percent mass to mass is the mass of the solute over the mass of the solution times 100%. The important part of this formula is actually the bottom here. And that is to remember that as we just talked about, a solution is made up of two things. It's made up of the solvent and the solute. And you do want to make sure that you get the mass of each of those. So it's a very common mistake people will make when they're using the formula, that they will actually only get the mass of the solvent and not the actual solution itself. Why is it a problem in these type of problems? More specifically for this type of problem, they typically will break up the mass of the solution into the mass of the solute and the mass of the solvent separately. So a lot of times people just see kind of like the bigger number and they go with that for the solution, but very often they will split it up. So you want to make sure that you do get both of those components or the bottom part of this calculation so that you get it. If you had a 4.5% by mass sodium chloride solution, that would mean also that you can turn this into sort of like a conversion factor that you could use in a dimensional analysis sort of problem. So if you have 4.5% mass to mass sodium chloride, that basically means that you have 4.5 grams of sodium chloride, 100 grams of solution. So you could take that percentage and really just turn it into like a conversion factor. You could also use it in the opposite way as well. You could flip it around and go 100 grams of solution over 4.5 grams of sodium chloride. So sometimes when you're doing these problems, it's easier or more convenient to do more of a dimensional analysis approach with the conversion factors, and you could kind of turn that percentage into kind of a usable conversion factor by just assuming 100 grams. Keep the numbers the same, and again, it makes it a little bit easier in the calculation as well. You obviously can just plug and chug into the equation as well, and it works out obviously the same way. It's helpful as well that you may not have to know the formula. You can kind of take that dimensional analysis approach and figure it out. There are some other percent concentrations as well, and there's percent volume to volume. So this is percent volume to volume. And that is the volume of the solute divided by the volume of the solution times 100%. This is typically like milliliters over milliliters is kind of the units there. And that's like the percentage like of alcohol and stuff like that. Percent by volume is that sort of calculation. We also have percent mass to volume. So this is the percent mass to volume. And that is the mass of the solute, the smaller part of the solution, divided by the volume of the solution times 100%. So unlike sort of the percent mass to mass on the previous slide, this one here, you really don't usually have to worry too much about. They oftentimes will in problems just give you the volume of the solution or you're able to figure it out. They don't usually break it up like they do kind of with the mass of the solute and the solvent. Just like the other one, if you had a 4.5% by volume sodium chloride solution, that would mean if you wanted to kind of turn it into a conversion factor, that would mean you would have 4.5 milliliters of sodium chloride in 100 milliliters of solution. And again, just like any conversion factor, you could flip it around and use it in the other direction. 100 milliliters of solution would give you 4.5 milliliters of sodium chloride. So once again, you could kind of turn that percentage into a usable conversion factor. You could also do it for this guy as well. If you had a 4.5% mass to volume, almost like density is kind of what this is, grams per milliliter is sort of the units associated. You would have of sodium chloride, you would have 4.5 grams of sodium chloride in 100 milliliters of solution, or flip it around, 100 milliliters of solution would contain 4.5 grams of sodium chloride. So for all these percent sort of concentrations, if you're given it, you can take a more dimensional analysis approach by turning that into a conversion factor. And again, sometimes it's a little bit easier to sort of do the calculation there. Any questions on any of those there? So why don't we try one here? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of calcium chloride in the solution. So we're looking for what is the percent mass to mass here. Yeah. Give it a go. Okay, let's take a look. So in this case, we're looking for the percent mass to mass. And this is the mass of the solute divided by the mass of the solution times 100%. In this case, we have 2.5 grams of calcium chloride. That would be our solute. That is the smaller part of the solution. Here, water would actually be our solvent in this case. So our mass of our solute, which is our smaller part of the solution, 2.5 grams, and the mass of the solvent is 50 grams of our water. Remember, though, that the solution is both of those things together, so we do need to add those together to get the mass of the solution, and that would get us 52.5 grams. So here, we do not want to just divide by the 50, which is only the solvent. So we'll do our percent mass to mass. That's going to give us 2.5 grams divided by 52.5 grams times 100%. And that's going to get us here, looks like 4.76%. You can leave this as a percent. A lot of times people will write M/M to indicate that it's mass to mass. And you can put sodium, not calcium chloride, calcium chloride here if you like as well. The grams actually cancel out, so none of those gram units still remain there, and the answers are just kind of percentage at this point. Any questions on that there? Okay. Let's take a look at another one then. Concentrated hydrochloric acid contains 37.2% by mass HCl. What is the mass of HCl in 35.5 grams of concentrated hydrochloric acid? So we're looking for the mass of the HCl in this case. So give it a go, see what you come up with. Okay, let's take a look. So we are looking, we're going to definitely use our mass percent here. So we have our mass of our solutes, our mass of our solution times 100%. In this particular case, we are given the mass percent. So we do know that is 37.2%. We're looking for the mass of the solute in this case, which is the HCl. Remember that if you have an HCl solution, HCl is the solute, just like if you had a sodium chloride solution, sodium chloride is the solute. So since we're looking for the HCl in this case, that would tell us we're actually looking for the solute. That would also tell us that the second number there is actually the mass of the solution in this case. So pretty much the name of any solution is usually the solute that is in that solution, and that's going to be 35.5 grams. So you could definitely just plug and chug into the equation here, as you do have obviously the percent mass to mass. You do have the mass of the solution, so you could solve for the mass of the solute in this case. You could also, though, take a dimensional analysis approach where maybe you don't have to rearrange that equation or maybe even remember the equation per se. And I'm going to take that approach just to kind of show you. So because we do have the percentage given to us, we could really just turn that into a conversion factor. And that would mean in this case, we have 37.2 grams of HCl in 100 grams of solution. And remember, since it is a conversion factor, we could flip it around and do the other way. 100 grams of solution is 37.2 grams of HCl in this particular case. So since we do have the mass of the solution given to us, we could just do our normal sort of dimensional analysis. So we could go with our 35.5 grams of solution. And again, just doing dimensional analysis, opposites cancel. So we would use the conversion factor like this that has solution on the bottom. HCl would be up on top. And now our grams of solution are going to cancel. And that's going to leave us now with what we're looking for in this case, which is about 13.2 grams of HCl. So here with more of a dimensional analysis approach, you didn't really have to remember per se this formula. You could just kind of do get rid of the units you don't want, keep the units you do want, and you get obviously the right answers. So you could also plug it into here, like I said before, and you would obviously get the same answer. It's really the same math because you'd be multiplying the solution to the other side, which is basically what you did there. And you'd be dividing by 100, which is basically what's on the bottom. So it's the exact same math, but maybe a little bit easier to maybe figure out instead of rearranging the formula. Any questions on that there? All right, then the next sort of unit of concentration we're going to talk about for solutions is probably the most popular unit, if you will, and most common unit, and that's molarity. And molarity is abbreviated with a big M. So if you see a big M next to a number, that stands for molarity. And molarity is really moles of solute over liters of solution. You could think of molarity as like a formula because we very often will solve for any of these three things in it. So molarity is equal to moles over liters. If you want liters, that is equal to moles divided by the molarity. And lastly, if you want moles, which is a very common use of molarity, that is liters times molarity. That is also a very important thing to remember that the volume does need to be in liters when you are using it with molarity. Otherwise, you will be off by a factor of probably 1,000 because very commonly, like in the laboratory, we measure volume a lot of times in milliliters. So the 1,000 milliliters to 1 liter conversion is used a lot with molarity to convert your volume oftentimes either from liters to milliliters or liters or milliliters to liters in here. But it definitely should always be in liters when you're using it with molarity. So you definitely want to do that. Because if you take milliliters and you times it by molarity, you actually get millimoles. So you'll be off by a factor of 1,000. So again, if you don't do that conversion, you won't get really what you're probably looking for, which is moles. So you definitely want to make sure that it is definitely in liters here when you do that. Moles as well, we could get to a lot of times. Also, grams to moles conversion is used a lot with molarity. And a reminder, that's the molar mass from the periodic table that we use to do that conversion. And if you have a 4.5 molar sodium chloride solution, it is very much recommended that when you use molarity in a calculation, you get rid of the big M. And that's because when people leave it with the big M in calculations, they very often forget all about the volume part. They don't even remember there is volume. All they see is M and they think moles and they don't know about liters or the volume part of it. So this directly will convert into 4.50 moles per liter of sodium chloride. So the number always stays with the moles, it's always per 1 liter. And that's really how you should use it in a calculation so you could clearly see both units, the moles and the liters, and you understand where they're at. You could also use it as a conversion factor, which means you could use it like I wrote it above, but if you needed to, you could also flip it the other way and once again take a dimensional analysis approach and just look at the units and cancel out the units. So highly recommend you kind of get rid of the big M and use both units so that you can see the volume. It's a very, very common error, like I said, that people really have no idea about the volume of it or what's going on with it, or even if there is a volume, because they just see the big M and for some reason think moles only because of the M. Now, if you do have a solution that is 1 molar sodium chloride, that means that you can have a solution that's made up of 1 mole sodium chloride and enough water basically to make 1 liter of solution. Now, one of the things that occurs when we talk about molarity is sometimes with ionic compounds and solutions, we may be interested in like the ions that are present, what their concentration is, rather than the entire thing. So as you can see there, we could say that we have 1 mole sodium ions and also 1 mole chloride ions, and their concentrations would be the same. So when we look at a ionic compound solution there, and we have something like 1 molar sodium chloride. Because that is a solution, it's a strong electrolyte, it will completely break apart in solution as sodium ions and chloride ions. So you got basically 100% in solution of just the ions floating around. So as I mentioned, sometimes we are interested in maybe just the sodium ion, or maybe we're just interested in the chloride ion, and we might need the concentration of those guys. And the way that works is kind of like stoichiometry is essentially how it works. If I know the molarity of the whole thing together, it is a 1-to-1 relationship between the whole thing and the sodium ion. That means, in terms of what happens with the molarity, you would take 1 times the concentration. And in this case, we would have 1 molar sodium ions floating around in that solution. You could do the same thing from the whole thing to the other ion, which is chloride in this case. And it is a 1-to-1 relationship. And you would take 1 times the molarity. And we would also have 1 molar chloride ions floating around. So we'd have the same concentration of each of those ions floating around the solution. Now, if I took calcium chloride solution, and it was a 1 molar solution, when calcium chloride breaks apart in solution, we will get a calcium ion, and we'll get a couple of chloride ions basically breaking apart. And in this case, if we're interested in the concentration of calcium, it is a 1-to-1 relationship between them, which means it would be 1 times 1 molar. And this solution would be 1 molar of calcium ions floating around. But when we look at the whole thing to chloride, it is a 1-to-2 relationship there. And what we do with concentration is we would take concentration, multiply it by 2, and that would give us that we have 2 molar chloride ions in this case. Concentrations are not additive, so obviously 2 and 1 doesn't equal 1. But if you think about what's happening here with, say, sodium chloride, when it goes for a swim, you get a sodium ion and a chloride ion. You get equal amounts of those ions in that solution, so they're equally concentrated. But when calcium chloride goes for a swim, you get 1 calcium ion and you get twice as much chloride ions floating around than you do calcium. So the concentration of chloride is twice as much as it is for calcium. Any questions on that there? So that is the quick way to figure out basically the concentration of an ion in a solution. If you know the concentration of the whole solution, you can kind of do like a stoichiometry, quick calculation of it. The actual calculation is actually this, just to show you how we actually get there. You would take the original concentration of 1 mole per liter, and again, I'm getting rid of the big M, so that big M is moles per liter. So just substituting that in there. And we would actually do the stoichiometry mole to mole relationship. It is a 1 mole to 1 mole relationship. So for 1 mole of the whole thing, I get 1 mole of calcium ions. Moles of the whole thing cancel, leaves me with 1 mole per liter of calcium ions, which is how we get to this concentration. If we did the same thing for our other one, starting with the original concentration, once again, it is a 1 mole to 2 mole relationship. So 1 mole of the whole thing gives me 2 moles of the chloride. And again, moles of the whole thing cancel, giving me 2 moles per liter of the chloride ion. So this is the long sort of stoichiometry calculation. The quick way you could get it is basically just multiply by the coefficient of the ion, and that will give you the concentration of just the ions that are present. Any questions on that? So that is how concentration or molarity relates to individual ions. All right, so why don't we try one here? Calculate the molarity of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters potassium 3910, I believe. And look, we're looking for the molarity, which is moles per liter. So we want to think about, do we have any of this information? We are given 15.6 grams of KBr. That's obviously not moles, but we definitely could get to moles using the molar mass from the periodic table. So we could eventually get there. We do have a volume of 1.25 liters. It's in liters, so that's good. So that is the bottom part here. So really what we need to do is just convert our grams into moles, and then we can figure out our molarity. So to do that there, we'll go 15.6 grams of the KBr. We'll go to periodic table. Looks like we just need to add those together. We'll get 119 grams per mole. And we're going to use our molar mass and divide by it so the grams cancel. And that's going to get us here, looks like, I'll call it 0.1311 moles. That is the top part here that we need. So now that we got both of them, the molarity should be 0.1311 moles divided by 1.25 liters. And that's going to get us 0.105. Now, in terms of the units, they don't cancel, so you can leave it one of two ways. You can leave the moles up on top divided by liters, whatever this is, KBr. You could, at this point, if you wanted to, turn that back into that big M KBr as well. So at the end of the calculation, you could turn it into the big M and leave it that way as well. Any questions on that there? So basically what this means is if you weighed out 15.6 grams of KBr and you put it in there with enough water to make 125 liters of solution, gave it a really good mixing and dissolved it all, you should then have a solution sitting there with 0.15 molar in terms of its concentration. Any questions on it there? All right, so I want you to try this one. What is the mass of sodium nitrate that you need to make 2.5 liters of a 0.15 molar solution of sodium nitrate? So sodium is 2299, nitrogen is 1401, and oxygen is 16. So we know that is moles per liter. And we're looking for grams of the sodium nitrate. And we have a volume of 2.5 liters. Again, it's in liters. Remember, it does need to be in liters for everything to work out right. If it's in milliliters, you do need to do that conversion. So we do have the bottom part there. We also have the molarity given to us, 0.15 molar sodium nitrate. So we do have the molarity. So ultimately here, the only thing we don't have is moles, which makes a good idea to start with, because from moles we can go to grams by using the molar mass, again, from the periodic table. So I'm going to, again, because I am given the molarity here, I'm going to do more of a dimensional analysis. I'm going to get rid of the big M and kind of put both units in there so I can see them. So that would be 0.15 moles per liter of sodium nitrate. And again, you could use it like a conversion factor. So if you needed, you could also flip it around and do liters over 0.15 moles of sodium nitrate. So again, you may not even have to worry about rearranging this equation correctly. I'm just going to kind of do a dimensional analysis approach. So I do have 2.5 liters. I want to get rid of liters and end with moles. So I will use it as the conversion factor here, where liters is in the opposite position on the bottom. That is going to allow my liters to cancel, and that's going to leave me moles in this case. So that will be 2.5 times 0.15. Going to give me 0.375 moles of sodium nitrate. Now that I did that, I basically just need to add my stuff together here. So I'm going to add those plus 3 times my oxygens, right? So that's going to get me there. Looks like 85 grams per mole. And we're going to use that again, dimensional analysis. Moles are on top. Moles need to go on the bottom so they properly cancel. And that will end me here with about 31.9 grams of sodium nitrate. Let's up any questions on the calculation here. Again, what this number means is if you weighed out 31.9 grams of sodium nitrate and you tossed it into a beaker that had about 2.5 liters of water, you pop it in there. Again, you mix it really well, get all that to dissolve. You should then again have a solution that has a molarity of 0.15 molar, basically, in this case. Any questions on that there? All right, so let's take a look at these. And here we are interested in maybe the concentrations of the ions in each of these solutions. So this is our first solution, 1.2 molar sodium sulfate. We're looking for what is the molarity of just the sodium ions and the sulfate ions in that solution. And for the second solution, it's 0.75 molar potassium chromate, and we're looking for what is the molarity of the ions in that solution, which is the potassium ions and the chromate ions. So why don't you take a moment there to see what you come up with. Okay, so let's take a look again. If we have the concentration of the entire solution, and we're interested in the ions here, since they are going to break apart, we just want to think about how they're going to break apart. So we'll take a look here maybe at, oops, zoom in. Take a look at this one here. So we have sodium sulfate solution. Because it's a strong electrolyte, it will break apart into two sodium ions in solution and sulfate. So basically, in that solution, you're going to get some couple of sulfate, a couple of sodiums and a sulfate happening for every one that goes in. So since the concentration here is 1.2 molar, it is a 1 to 2 relationship between the sodium ion and the whole thing. So we would just multiply the whole concentration by 2, and that would tell us that it is 2.4 molar in terms of sodium ions in that solution. We would do the same thing for our sulfate, but it is a 1 to 1 relationship. And we would take 1 times 1.2 molar, and that's going to give us 1.2 molar of the sulfate ions. And as you can see here, you get basically 2-for-1 deal. So you get twice as much sodium in that solution for every sulfate. So the concentration of sodium is twice that of sulfate in here. Any questions on that one there? Same thing here for the second one, a little potassium chromate. When that breaks apart, we're going to get a couple of potassiums. and a chromate. And again, same idea here. If we were kind of looking in the solution, we'll have a couple of potassiums per one chromate that comes out. And that means if this is 0.75 molar, again, it's a 1 to 2 relationship here. So we're going to go 2 times 0.75 molar, giving us 1.50 molar of potassium ions floating around that solution. It is 1 to 1 in terms of the chromate. So we'll take 1 times 0.75 molar, giving us 0.75 molar of our chromate in this case. And same idea as above. We got basically twice as much potassium per every one that goes in there for one chromate. Any questions on either of those there? All right, so let's take a look here then. In this problem, we want to know how many moles of calcium and how many moles of chloride ions are there in 42 milliliters. Okay, so let's take a look. You can really do this one of two ways. You can either get the concentration of the ions to begin with, or you could kind of do it at the end. It's sort of up to you. I'm going to do it at the beginning. So in this case, we are definitely dealing still with molarity, which is moles per liter. We are given a volume. It is not in liters, but we do have a volume, and we are given the molarity. So we are ultimately going to sort of rearrange this equation and use it to solve for moles here. Now, since we do have the molarity given to us here of 0.35 molar calcium chloride, and we're not interested in the whole thing, but we're interested in kind of the individual ions here, we could do what we just did, which is we could just figure out how this guy's going to break apart. And it should break apart into a calcium ion and two chloride ions. And that means that if the concentration of the whole thing is 0.35 molar, it is a 1 to 1 relationship between that and the calcium, which means if I take 1 times 0.35 molar, will tell me it is 0.35 molar calcium ions. I could also do it for the other one. It's a 1 to 2 relationship here. And that means that I'll take 2 times 0.350 molar. And that will tell me that I got here 0.7, looks like, molar chloride ions. So now that I have the concentration of each ion, I could really just do this calculation for each of them and end up with the moles. I am again going to get rid of the big M here and turn that into 0.35 moles per liter calcium ions and turn this guy into 0.75, oops, too many zeros, moles per liter of chloride ions. So that way I could see both units. That way it will also hopefully remind you that, oh yes, my volume does need to be in liters here to properly cancel out as opposed to milliliters, which is what I got going on here. So I do need to do that conversion of 42 milliliters into liters. There's 1,000 milliliters in 1 liter. That's going to give me 0.0420 liters in this case. So now that I have my volume there converted into liters, I could actually do my calculation here for each of them. I'll go a little higher up here and do it. So taking the volume in liters, 0.0420 liters. I am again just going to kind of use dimensional analysis here. So my liters are on the bottom, so that's good. So we'll just multiply in this case. The liters will cancel, and that's going to give me here 0.042 times 0.35. Looks like 0.0147 moles of calcium ions. We'll do the same thing for our other one. So we have the same volumes because it's in the same beaker or whatever it may be in at that point. We'll use our concentration here of this one, which is 0.7 moles per liter of our chloride ions. And that's going to get us 0.042 times 0.7, 0.0294 moles of chloride. Once again, this does make sense if you think about it. For every one of those guys that go for a swim, you get one calcium ion and you get twice as much chloride ions. So you got twice the concentration, twice the moles here of chloride floating around than you do calcium floating around in that solution. Any questions on that there? The other way you could have done it is just to have used the whole thing's molarity and figured out the moles of the whole thing by using the molarity of the whole thing, which was 0.35 moles per liter. That would give you moles of the calcium chloride. And then you can basically just do a mole to mole sort of calculation from here, and that would get you there as well. So that would work. Question on that one there. All right, the next thing we're going to talk about is dilution. And dilution is the process where we take a solution that is more concentrated, has a lot more solute dissolved in it, and typically we add more solvent to it, like water, and that will lower its concentration. Now, when we do a dilution, because we're only really adding water or a solvent, the moles of the solute before and after dilution will remain the same. Why does the molarity go down? Because the molarity, as we just saw, is moles of solute divided by liters of solution. And remember, again, the solution is the solute plus the solvent. So when we do a dilution, we're adding more solvent, so we're adding more of this guy, which means the bottom part here gets larger, and that brings our molarity down because we're dividing by a larger number on the bottom there. So by doing a dilution, we're increasing the volume of solution, and that will bring the molarity down to a lower number, a more diluted concentration. Now, there is a way that you do that. You can take a little bit of water, take your more concentrated solution, put it in there, top it off with some more water. This is a volumetric flask. It has one line which represents the volume, so you would fill it up slowly, slowly, slowly. You definitely don't want to go above the line, and you would want to fill it with water all the way to that line and put the cap on it there and do some mixing, and you will have your more diluted solution. As you can see, not as dark of a green color over here because it is diluted down with a lot of water in this particular case. There is a formula that is used to calculate dilutions, and most people will use this formula here, which is M1V1 equals M2V2. This is usually before the dilution, so the more concentrated solution. This is usually after the dilution. That M is molarity on both sides, and the V is volume on both sides. Now, if you are using this equation here, which is the dilution equation, when we talked about molarity a second ago, I did say that if you are going to use molarity and volume together, it should be in liters, and it should be, but it will work out okay if you are specifically using this equation and you want to leave your volume in milliliters on both sides. It will work out just fine. So in this equation only, if you want to leave volume in milliliters, that's okay. It will work out. You could also convert it to liters. That will work out as well. It should be okay. The reason that works out is, let's just say I was solving for M1, that would be M2V2 divided by V1. We put in our units, molarity, and I leave my volume in milliliters on top and bottom. they cancel out each other, so everything's good and nothing bad will happen. If you put the volume in milliliters and you're solving for a volume, your answer will be in milliliters as well. But you could also use liters if you like as well here. But definitely, if you're just using molarity by itself in a non-dilution situation, the volume does need to be in liters for sure. So just keep that in mind. Now, there is a more generic formula, which is C1V1 equals C2V2, that sometimes people will use for this. The C here is just a generic concentration unit. So technically speaking, if you wanted to, you could do this calculation with like percent mass to mass that we talked about earlier, percent volume to volume that we did earlier. But most people will use the one on the left because molarity is the most common unit of concentration. So most often they will definitely kind of use the guy there on the left. So let's take a look at one here together. What is the volume of 19 molar sodium hydroxide that must be used to prepare 1 liter of 0.15 molar sodium hydroxide solution? So basically, we have a sodium hydroxide solution that is 19 molar, and we want to make a sodium hydroxide solution that is 0.15 molar. That is less concentrated. There is no reaction happening here. We're just doing a dilution, sodium hydroxide, sodium hydroxide. So basically, we have a bottle sitting there that is 19 molar sodium hydroxide. We want to make like a new container, beaker, whatever it may be, that is 1 liter in volume and has a molarity of 0.15 molar. So we could use our dilution equation, M1V1 equals M2V2. In this case, the more concentrated one would typically be M1. This would be M2. This would be V2. And that means that we really are looking for V1 in this case. This is the only thing we don't have. So if I put into this formula, I'm going to solve for V1, which means I'm going to divide that to the other side. And that will give me M2 V2 divided by M1. Putting in my numbers, I will end up with M2, which is 0.15 molar. My V2, it is okay here to leave it in liters, and that works. And we're going to divide it here by 19 molar. So the molarity are going to cancel, and that's going to be me liters. So 0.15 times 1 divided by 19 will give me something like 0.00789 liters. Or if I want maybe an easier unit, that is 7.89 milliliters. What does that 7.89 milliliters mean? That is how much of this more concentrated solution you would go and take out. So you would go over to your bottle of 19 molar, you would pull out and put in there 7.89 milliliters of the more concentrated solution. Now remember that the total volume of our new solution we are looking for is 1 liter or 1,000 milliliters in this case. Would I put 1,000 milliliters of water in there with that? The answer is you would not, because you would then end up with 1,007 milliliters total volume, and that would be too much. So oftentimes in dilution problems, we're interested in how much water we need to add. And how much water in this case would be usually V2 minus V1. So we know that V2 is 1,000 milliliters or 1 liter minus what I already put in there, which is 7.89 milliliters. And that will tell me that if I do that, I should put in there 992.11 milliliters of water with it. So I would put in here 992.11 milliliters of water. And if I give it a good mixing, I will now have a solution that's 1,000 milliliters or 1 liter in volume. and it should be a concentration of 0.15 molar. So typically, if you solve for V1, that is how much of the stronger, more concentrated solution you're going to put in there. But very commonly in these type of problems, they oftentimes are interested and ask about how much water or something you need to add to it. And that usually is always kind of V2 minus V1 will tell you how much water you need to add. Any questions on that there? All right, lay it up there.